So how the kernel of the operating system acts as the interrupt handler and how interrupt handling is used to manage low-level scheduling under the purpose of operating system and related to multitasking and concepts of multitasking with the process states. Now, the CPU will check for interrupt signals after every single fetch decode execute cycle. The system will enter the kernel mode if any of the following type of interrupt signals are sent. Number one, device interrupt. For example, printer out of paper, device not present, and so on. And then second one is exception. Let me share it. Exceptions are, for example, instruction faults such as division by zero, unidentified opcode, stack fault, and any of those faults which basically make the program break. Those are called exceptions. And then software interrupts. Software interrupts are sometimes called traps. For example, process requesting a resource such as hard disk drive. So when an interrupt is received, so these are the types of interrupts. Handled by the kernel of the operating system. So when an interrupt is received, the kernel will consult the interrupt dispatch table. Interrupt dispatch table or IDT. So when an interrupt is received, the kernel will consult the interrupt dispatch table. This table links a device description with the appropriate interrupt routine. So this table basically maintains that which device is basically related to which interrupt is related to which device, so that proper device handler or the device driver could be fetched. So IDT will supply the address of the low-level routine to handle the interrupt event received. The kernel will save the state of the interrupt process on the kernel stack. The stack basically over which the current position of the program and its related registers data is stored is basically the data structure. The kernel will save the state of the interrupt processes on the kernel stack, and process state will restore once the interrupt task is serviced. Interrupts will be prioritized using interrupt priority levels. So every interrupt has their own priority level. According to those priority levels, interrupts are prioritized. The process is suspended only if it is interrupt priority level is greater than that of the current task. So if an interrupt is generated, the system will evaluate that whether the process related to the interrupt is having higher priority. So if it is, then it will be uh, interrupted. Otherwise, the whole process will go on. The process with the lower interrupt priority level is saved in the interrupt register and is handled or serviced when IPL value falls to a certain level. Examples of interrupt priority levels include interrupt priority levels include power fail interrupt, clock interrupt, system clock. Third one is, let's say, IO devices interrupt. All right. So let's summarize this it all, how basically it works. So interrupt process. How it happens. So interrupt is received. Other interrupts are then disabled. So that the process that deals with the interrupts cannot itself be interrupted. So interrupt when it is received, other interrupts are disabled. So this is step number one. Then comes the state of current task is saved. The state of current task operating is saved on the kernel stack. Stack is a memory data structure, and if it is related to the kernel, then it is called kernel data structure. So then the source of the interrupt is identified. The source of the interrupt is identified. Now, for example, is it hardware or an exception or software interrupt? The priority of the interrupt is then checked. All right. Now, the system now jumps to the interrupt service routine. And it is basically loaded using interrupt dispatch table, IDT. For example, it may be necessary to display an error message on the user screen and all, so this will be all decided at this level. Now, once completed, the state of the interrupt task is restored using the values saved on the kernel stack. The process then continues. After completing servicing the interrupt, previous job is reloaded from stack and it continues. All right, so All right, and the last thing would be after an interrupt has been handled, the interrupt needs to be restored so that any further interrupts can be dealt with. All right, that is how the whole thing works. So this is basically an addition to the previous understanding of ours. So interrupt is received, other interrupts are then disabled, the state of current task is saved on the kernel stack, the source of the interrupt is identified, the priority is checked. If the priority is low, then the current task continues. If the priority is high, then interrupt service routine is called and loaded using IDT, interrupt dispatch table. After completing servicing the interrupt, previous job is reloaded from the stack and the job is continued, and interrupts which were disabled earlier are now restored. So that's about it for interrupt handling with the help of kernels. It is nothing but an addition of what we have studied in uh,